Hey Pre-Calc, welcome back. Hope y'all are well. Our objective today is going to be to start solving exponential and log equations today. So now hopefully we can see why we need logarithms and the types of equations we're able to solve that we can't unless we have logs. So I've got the checklist on the screen. You know what to do from here. All right, you don't need to write anything down, but would you try this warm up in your head? Hit continue when you are ready to check your answers. All right, answers are on the screen. The moral of the story is that ln and e are inverses of each other, so they have this undoing or this cancellation effect on each other when they are right next to one another. All right. Force another pause on the screen. Can you go ahead and copy the two examples for me? Okay, so we're going to look at exponential and log equations today, meaning we're going to look at equations where the unknown is both in the exponent, that would be an exponential equation, and inside the log, so that would be a log equation. The first method for exponentials is when you can make the base the same, and we typically do this when you've got unknowns in both exponents. Okay, so in this case, we try to see if we can make the base the same. For example, in this first one, we have 5 to the 2x equals 5 to the x minus 4. So 2x, this exponent, must equal this exponent, right? So if I subtract 1 from both sides, I get that x equals -4. And of course, we can always check our answers in algebra, right? Plugging -4 back in. On the left side, I get 5 to the -8, and that's exactly what I get on the right side, okay? Now, for the second example, notice that our bases are not the same, okay? However, I can write 16 as a power of this base, as a power of 4. So that's what I'm going to do first. So I'm going to keep the left side as is, because what I can do is write the right base as a power of 4. So that is the same as 4 squared, and then I still have this power of 3x squared minus 6, right? Now, let's be careful. Let's go ahead and clean this up a little bit. Let's keep the left side as is. But remember, when you have a power to a power, what do? We multiply them. So this is the same as 4 to the 6x squared minus 12, right? Be sure you take this 2 and distribute it to both terms here. And now we're back to what we had on the left side, where we've got same bases, so now we can equate the exponents. So x squared minus 2 is equal to 6x squared minus 12. I'm going to let you go ahead and solve that for x. Hit continue when you're ready to check your answer. All right, so I'm getting plus or minus square root of 2 for x. If that's not what you got, go ahead and pause and make any corrections. I'm forcing another pause on the screen. Can you go ahead and copy the next two equations for me? All right, so method 2, what if I can't make the bases the same, right? Like 27, I can't write nicely as a base of 5. Well, our second method, when we can't make the bases the same, is going to be to take the log of both sides, because remember, logs and exponentials are inverses of each other, okay? So what we're going to do typically is take the log base of whatever this base is. So I'm going to take log base 5 of both sides. So log base 5 of 5 to the x minus 2, and what I do to one side I have to do to the other. So that equals log base 5 of 27, okay? Now, why did I do that? Well, when you have, remember, exponentials and logs are inverses when their bases are the same. So when you have a log and an exponential piece right next to each other, and their bases are the same, these cancel, and you're left with just x minus 2 on the left. And then on the right, you have log base 5 of 27, which we can plug into the calculator. I'll show you how to in just a bit. So as an exact answer, x equals log base 5 of 27 plus 2. Let me show you how to type that in both an 84 and Desmos. So for the 84, we are going to go alpha window. You're going to access your F2 menu, and see number 5 is log base, so you're going to go log base 5, right arrow, of 27, right arrow out of the argument, plus 2. And I'm getting about 4, so always round to 3 decimal places unless directions say otherwise. So we'll put 4.048. Now we can test that, right? If I take 5 to that power minus 2, so if I do this, and I go to the answer, which is second negative, okay? And then minus 2, I'm just plugging x back in here. I should get 27, and there it is, okay? So x is 4.048. Now, if you're in Desmos, let's come over here. You're going to type in log, just L-O-G, then do shift minus, and that will give an underscore for you, a base. So your base is 5. Then you're going to right arrow, parentheses 27, and then plus 2. And there's that value we got as well. All right, for this next one, notice it's a little different for a couple reasons. First of all, your base is e instead of 5, and second is that your exponential piece has not been isolated yet. Okay, so let's isolate this part that I underlined by dividing both sides by 50. So I have e to the negative 2x equals 13 over 50. All right, to get an exponent out of the exponent, we use logs, okay? So this time I want to use log base what? I want to use log base e, which is which log? ln. So I'm going to take ln of the left side, and what I do to one side I have to do to the other, right? ln of 13 over 50. All right, now what does the left side reduce to? Just negative 2x, right? Take a look at our warm-up. When ln and e are right next to each other, we just get that exponent back. You can also think of this as a power rule. Fly that negative 2x forward, and then you have just times ln of e, which is 1. So negative 2x on the left. On the right, I have ln of 13 over 50, which I can type into the calculator. So x is going to equal ln, maybe, x will be ln of 13 over 50 divided by negative 2. And if you want that as a decimal, we get 0.674. And place another pause on your screen. Go ahead and copy the 2 examples I have. All right, so we kind of have 2 methods with log equations, just like we do with exponentials. So our first method for exponentials was, hey, if we have the same base on both sides, we can just put the insides equal to each other. Kind of same idea here. If we have the same log on both sides, we can just put our insides equal to each other. In other words, if there's a log in every single term, we can get one log on each side and then go ahead and just set the insides equal to each other. So for example here, I have log base 12 of x equals log base 12 of x squared minus 6. So this tells me I can just set x equal to x squared minus 6, right? What kind of equation is this now? This is a quadratic, so let's get everything on one side and see if we can factor. So this would factor into x minus 3, x plus 2. So x is going to be positive 3 and negative 2. Now here's something you have to watch out for with logarithmic equations is you may have extraneous solutions. These are solutions that pop up. They're like extra solutions that actually don't work, okay? So with log equations, you've got to go and make sure that these x's actually do yield a true statement. So let's test 3. Well, if I put 3 in for x here, I get log base 12 of 3. If I input 3 here, I get log base 12 of 9 minus 6, which is log base 12 of 3. So 3 works. I'm going to keep it. Let's test negative 2. Well, as soon as I try negative 2, I've got some issues because I get log base 12 of negative 2. And can we take log of a negative number? No, we cannot take log of a negative. We cannot take log of 0. Our inputs must be, our arguments must be positive, okay? So I am going to toss that negative 2. It's an extraneous solution, and I end up with just x equals 3. All right, for the second one, let's first go ahead and move this log to the other side. So we've got 2 log base 4 of x equals log base 4 of x plus 2. So I've got log base 4 on both sides, but the problem is I've got this extra 2 here. So any ideas what we can do there? We can apply the power rule and fly that 2 back to the power, okay? So I can rewrite the left side as log base 4 of x to the power of 2, and then I still have the right side as log base 4 of x plus 2. And now I've got a log base 4 on both sides, so now I can go ahead and equate the arguments, so set the insides equal to each other. So x squared equals x plus 2. What kind of equation do we have now? Quadratic, so let's get all our x's on one side, 0 on the other. We can factor this as x minus 2, x plus 1. So my possible solutions here are positive 2, negative 1. Let's go ahead and test these. So I can look at my options actually, and I can toss the negative 1 right away. Do you know why? So I put negative 1 in here. I'm taking log of a negative, and that is meaningless, okay? But let's test x equals 2. So if I test x equals 2, I get 2 log base 4 of 2. Remember, I can bring that 2 to the power. So I basically get log base 4 of 4 minus log base 4 of 2 plus 2, which is 4. So log base 4 of 4 minus log base 4 of 4 is indeed 0. So I'll keep x equals 2 as my only solution. First pause on the screen, go ahead and copy what I have. Okay, so for these types of logs, notice that we do not have a log on both sides. So we have some kind of other term here, in this case a constant. So when you don't have logs on both sides, what you're going to do is kind of like the analogous situation over here when we didn't have the same bases on both sides, we took log, right, of both sides. So here we're going to convert to exponential form, okay? So for this first one, we would have 3 to the 2 equals x squared minus 9. So I get 9 equals x squared minus 9. So x squared is 18. So x will be plus or minus square root of 18. And we can rationalize that if you want as plus or minus 3 square roots of 2. Make sure you do test these and to verify that they both work. And in this case, you will see that we can keep both solutions. Okay, now another way to do this actually would have been to write the right side as log base 3 of 9, right? Because 2 is log base 3 of 9. 2 is the power that we raise 3 to get 9. And then we could have set the insides equal to each other, which is exactly what we got at this step, and then we could keep going from there. Okay, for the second one, notice that I can't convert to log form or to exponential form from log form yet because I've got 2 logs. So any ideas? Let's condense this into one log using the product rule for logs. So I see plus on the outside. I can make this one log using multiplication on the inside. All right, so now I've got a log equals a number. So now what? Now let's convert to exponential form. So 3 to the 2 equals all of this. I'm going to go ahead, I think, and distribute that 4. So 4x minus 20. So I've got 9 equals 4x minus 20. So 4x equals 29. So x equals 29 divided by 4. We do need to check it. All right, so I tested just real quick plugging x into x right here, plugging 29 over 4 in for x here, typing that in, and I got 2, so it looks good. All right, the last kind of equations, we're going to look at log equations that we can solve graphically. So I'll first pause on your screen, go ahead and copy the equation. So what we do, and this is a really common way of solving equations on the calculator active section of the AP Calc exams, what we'll do is we'll put this side of the equation into y1 in our calculator, or in Desmos, just type it into line 1. And then on the other, on y2, we'll just graph y equals 2, okay? And then we want to see when y1 equals y2. In other words, we want to see where the graphs intersect. So let's go ahead and take a look at Desmos. So I've typed in the left side of the equation into line 1, or on the 84, put it in y1. And then on line 2, I'll graph y equals 2. And what I want to do is I want to see when these intersect. So I can see I need to expand my x's quite a bit. So as I expand here, I went to 200. I can see, here we go. Here's the intersection. 180.384 is my x value, so that would be my solution over here. So 180.384. If you're on the 84, once you graph, set your window, so make sure you expand your x max to go to maybe like 200. And then for the intersection, you'll go second trace number 5, and then get close to that intersection and hit enter 3 times. All right, so here's my wrap-up question for you. What do you think, true or false? Log of x plus log of x equals log x squared. So I can condense these by multiplying the insides, and x times x is indeed x squared. So I get log of x squared equals log of x squared, which certainly looks good. But let's pop over to Desmond's here to see what's going on. So here I've graphed in blue log of x plus log of x, so it's on the left side. Now here's log of x squared. It's not quite the same, right? Notice that log of x squared has what I'd call a larger domain than log of x plus log of x. And that is because when I square a negative number, I get a positive. So this allows me to have a larger domain. Now the two are the same for all positive x's, but they're not the same for all x's. And this kind of showcases why we get extraneous solutions when we apply our log properties, because we can get these statements that aren't true for all x's, only for certain x's. And so that's why we have to be real careful when we apply log properties to make sure that we didn't get any extraneous solutions. So always check your solutions. All right, you all, I will see you next time.